So since we can deal with equations now and solving for a variable, and then actually substituting back in and evaluating the equation at that value, we want to look more at formulas specifically, because sometimes more than one variable will be involved, and there may be more than one assignment to a variable. We might have two values, one for x, one for y, and then an unknown z. You never know. So we want to look closer at formulas. So a formula is a recipe for doing calculations. So a recipe tells you what to do, how to do it, and in what order, generally. So we evaluate the formula when we're plugging in values, like we've seen before when we're checking after we've solved. So we can evaluate a formula at a specific value for a variable. Okay, so we're going to do some examples. Suppose you see a lightning storm and a few seconds later you hear thunder. Your distance from the place where the lightning struck is given by the formula m equals 1/5 t, where t is the number of seconds from the lightning flash to the sound of the thunder. M is in miles. So, suppose it takes 12 seconds for the sound of thunder to reach you after you've seen the lightning. How far away is the storm? So what are we given and what is our unknown? We're evaluating, we have to plug in 12. 12 seconds is t, since t is the number of seconds from the lightning flash to the sound of thunder. And we're solving for m in miles. So m is equal to 1/5. That's the constant in our formula. And we're multiplying by t, which in this case is 12. So 12 divided by 5. That many miles away, but it feels funny to talk about fractional miles. So if we do the division, this is about 2.4 miles away. Okay. So now suppose that it took 16 seconds to reach you. Is the storm moving towards you or away from you, and how far away is it? So if it's taking longer for the sound to reach you, obviously it's farther away. It's moving away from you, but we want to know specifically what distance. So go ahead and take that one and solve. Do the long division and give me the number of miles as a decimal. So what do you get? 16 divided by 5, when we do the multiplication, is 3.2 miles away. And again, it's moving away from us. Moving away. Since now our distance is longer and it took longer, so it makes sense. All right, I thought my joke was funny. Go home, lightning, you're drunk. Doesn't even touch the ground. It just goes back up into itself. Another problem, the cost C of operating a microwave over 1 year is given by the formula C equals all that junk. W is the wattage, H is the number of hours used per day, E is the energy cost per kilowatt hour. We want to find the cost of operating a 1400 watt microwave for 0.3 hours per day if the energy cost is 15 cents per kilowatt hour. So we just have to plug in the correct pieces for our variables. So in the formula, W is the first thing up in the numerator. That is the wattage. So the wattage of our microwave in this case is 1400 watts. And multiplying to that is H. What is H? The number of hours used per day. So our time is in units of hours, so we can use 0.3 to multiply. If it wasn't, we would have to convert. If we had minutes, we would have to change it into hours to fit the formula's parameters. 365 is a constant in the formula, since we're dealing for a year, 365 days. And the other constant involved is that 1,000 in the denominator. Last thing we need is E, the energy cost per kilowatt hour. So in this case, it's 15 cents, and we're leaving it in the form of dollars for our units. All right, so what do we get after all of this? If we do the multiplication, it comes out to be $22.99. Actually, multiplying it and all of that isn't really the focus for right now, so I'm just going to tell you the value. I want to be sure that you can plug in the correct values for the correct variables and use the right units. And again, units on C is the cost of operation. So it makes sense that we should be in a dollar value. Okay, turning the page. Determine the cost of operating a 1,000 watt microwave for half an hour a day for 1 year if the energy cost is 11 cents per kilowatt hour. So what do you get there? So again, plugging in our kilowatt wattage is 1,000 watts. And my time per day that I'm using is for half an hour. We're still working with 1 year, 365 days. Still have that constant from the formula in the denominator. And in this case, the cost per kilowatt hour is 11 cents. So this one's a little bit simpler because my 1,000 divided by 1,000 is going to cancel. And it comes out to be around $20.08. So a little bit cheaper. Okay, so let's look at some more examples. Consider the formula S equals 4321X, where S is the number of socks of the average size that can be produced from X bales of cotton. You see a shipment of 350 bales. How many socks can be made from that amount of cotton? So we're given an amount of cotton. We want to figure out the number of socks we can make. So we're solving for S, and we have a value for X. So again, the constant involved, 4,321, and I need to multiply by what? How many bales of cotton do I have? 350. So before we actually solve those multiplications, what units are on S? What does S represent? The number of socks of average size. So whenever we're dealing with an application problem, we always have to have units on the end. Tell me, what am I dealing with? So when we do this multiplication, it's a really big number. Over 1 million. Although we don't know if it's pairs of socks or single socks. Either way, it's a lot. But this many socks can be made from 350 bales. So we always like to sum it up with a sentence, make sure to have units. We could have done the same for these examples. If I use a 1,400 watt microwave for 0.3 hours a day for a whole year and it costs me 15 cents per kilowatt hour, the annual cost is going to be around $23. But too much to write for right now. Okay, so try. Determine how many socks can be made from 70 bales of cotton. Obviously a lot less than this, since 70 is a lot less than 350. But tell me exactly, how many socks can I make from 70 bales? So, plugging it in. Again, we have our constant from the formula. We're multiplying by the number of bales of cotton that we have. Doing the multiplication, 302,470 socks can be made from 70 bales. Now let's suppose the sock company wants to know how many bales of cotton they need to order to produce a certain number of socks. So that first example, again, we'll just assume we want to produce 230,000 socks. How do they go about this? How do they solve for that? So in this case, our number of socks is given to us. I want to make this many socks. Here's my constant that's involved in the formula. I want to figure out X. I want to know how many bales of cotton I need in order to make that many socks. So to solve for X, what do we need to do? I have 4,321 attached by multiplication. So I need to divide on both sides to get rid of it. And X is going to be equal to 53.2 bales. But just thinking about producing something, can you order 0.2 of a bale of cotton? doesn't work that way. So in this case, we need to round up or down. So I have to be able to produce that 230,000 socks. I can't make any less, so I need to bump that up to 54 bales of hay. So I need 54 bales to make that quota. I'll have a little extra with this, but if I only buy 53, we aren't going to make that quota. It'll be less than that. Okay. But let's just say I'm giving you spitting off a bunch of different amounts of socks that I want to produce. We don't want to have to do this solving process every single time. So we want to be able to take our formula and solve it generically for the variable that we're looking for. So generically, let's solve s equals 4321x for x. So before, when we were given bales of cotton, spits out the number of socks really fast. But if I'm having a number of socks and trying to solve for the number of bales, then we have to do this process every single time. But if we take care of it in the beginning, then it doesn't matter. We can plug in s and get x really fast. So again, to get this guy on its own, we have to do the same thing. Divide by 4321 on both sides. So x is equal to number of socks divided by 4321. So if we can recognize that in the beginning, instead of having to do the division, move it over every single time, we can just plug it in, do the division, get out the value really fast. Okay, so we're going to be given some formulas next, and we want to be able to solve for some specific variable that's given. So the first example, we have h is equal to 18z. And I want to solve that for z. So I want to get z on its own. What has to happen? So z is attached to a fraction out on the front. So instead of dividing by a fraction, what should we do? Multiply by what on both sides? Reciprocal of 1/8 gives me 8. Whatever I do to one side, I have to do to the other. Because again, multiplying by the reciprocal, what happens? 8 divided by 8 gives me 1. And I'm left with 8h. Okay, another one. Formula you will see pretty often is distance, rate, and time, how it's related. The DIRT formula. Distance equals rate times time. D equals RT, that's where we get that DIRT name from. We want to solve this for time. So right now he's attached to rate. So to get it on its own, we need to divide both sides by R. So these are equivalent, as are these two. But sometimes it's easier to work with the formula when, let's say, I have distance and rate, but I'm looking for time. It's going to be quicker to spit out here than trying to solve in the general DIRT formula, plugging it in, then evaluating. So sometimes it saves us time. Okay, next page, 2 for you to try. Solve the first one for Q, solve the second one for P. First one, we are trying to solve that for Q. He's attached to a fraction, so we want to multiply by what on both sides? Reciprocal of 2/3, which is 3/2. So Q is equal to what? These are going to cancel. And we'll be left with 3/2 D. In the second one, you were asked to solve for P. So, again, I want P on its own right now. He's attached to M. So we need to divide both sides by M. Because he'll cancel over here and he will move over. And we have P isolated. Sweet. Same thing can happen if we need to use addition or subtraction to isolate a variable. So in all of these cases, we decide to use multiplication and division. Same thing happens with subtraction. So first example, equation of a line. Right now I have y isolated. I want to solve for x. So what do we need to move? Him, he's positive over here, so we need to subtract to move him over. And now x is isolated. Okay. Same thing if we had subtraction in that next example quickly. If I want, thinking too fast. If I want x on its own, we have to move minus b. He is negative, so we need to add him to have it cancel over here and move to the other side. So regardless of with multiplication and division or addition and subtraction, we can still isolate a specific variable. You might even have some cases where you have to combine both steps. So next, I have ax plus b equals c. I want to solve that for x. So in this problem, what has to be taken care of first? If I'm trying to get x on its own, I need to have that term isolated before I can take care of a. So b has to move first. He's positive on this side, so I need to subtract him to move him over to the other. Now that that's happened, we have that x term on its own. Right now he's being multiplied by a, so we need to divide both sides by a to get x alone. And in that case, x is isolated. Okay, 2 for you to try. Take the next two, solve the first one for x, second one for q. So solving the first one for x, what has to be taken care of first? Trying to solve for x, so that term needs to be on its own. We have to move b to the other side. He's positive over here, so we need to subtract b from both sides. And our x term is then isolated. We need to divide both sides by m. So x is equal to y minus b divided by m. For the second one, you're asked to solve for q. So again, if I want that variable on its own, this term has to first be isolated. So what do we need to do to both sides? Add p to move it over. And we're trying to solve for q, so we need to divide both sides by t. So q is a plus p divided by t. Being able to solve generically in the beginning will help you in the long run. If I were to give you a bunch of y, b, and m values, for example, it's going to be faster to solve for x in this equivalent version of the equation than in the beginning, because you'll have to do those steps every single time.